Now let us discuss about the collisions in detail. That is elastic and inelastic collisions. Let us consider two masses m1 and m2, and m1 is moving along a straight line towards m2 with a velocity v1I. m2 is at rest. After collision, let the two masses move in the directions shown, making an angle of θ1 and θ2 with the x-axis with velocities v1f and v2f respectively. Considering the elastic collision in one dimension, total momentum before collision is equivalent to total momentum after collision, and total kinetic energy before collision is equivalent to total kinetic energy after collision. So, m1 v1I plus m2 v2I is equal to m1 v1f plus m2 v2f. Similarly, half m1 v1I square plus half m2 v2I square is equivalent to half m1 v1f square plus half m2 v2f square. From the above two equations, let us rearrange it and find an equation for v1f and v2f. Since the second mass was considered at rest, m2 will be equivalent to 0 in equations A and B. Hence, m1 v1I is equivalent to m1 v1f plus m2 v2f, and m1 v1I square is equivalent to m1 v1f square plus m2 v2f square. Taking m1 as a common factor from the first equation, we will get m1 into v1I minus v1f is equivalent to m2 v2f. Similarly, from the second equation, taking m1 as a common factor, m1 into v1I square minus v1f square is equivalent to m2 into v2f square. A square minus b square can be written as a plus b into a minus b. Hence, the LHS of equation 2 becomes m1 into v1I minus v1f into v1I plus v1f is equivalent to m2 into v2f square. Substituting for m2 from equation 1 and rearranging the terms, we will get the final velocities of the two objects after collision. So, v1f will be equivalent to m1 minus m2 divided by m1 plus m2 into v1I, and v2f will be equivalent to 2m1 divided by m1 plus m2 into v1I. So we have derived the final velocities of the two objects in terms of the initial velocity of the first object and the second object being at rest. Now let us consider two special cases. That is, when A and B are having similar masses, then A stops after the collision and B starts moving with the original speed of A. So in the previous case, let us put MA equivalent to MB. So we can see VA2x, that is, final velocity of the first object becomes 0 since MA is equivalent to MB, and in the second case it will become VB2x is equivalent to 2MA divided by MA plus MA, which is 2MA, that is VB2x is equivalent to VA1x. That is, second object starts moving with the velocity of the first and the first object comes to rest. Now let us take the second case. When B is much more massive than A, that is, second object is having a comparatively higher mass compared to the first object, then A reverses its velocity direction and B hardly moves. That is, VA2x will be approximately minus VA1x and VB2x will be equivalent to 0. Now taking the case of collisions in 2 dimensions, according to the conservation of momentum, we are taking the total momentum before collision is equivalent to total momentum after collision. So taking the first particle alone, which is moving with a velocity v, and the second particle being at rest, m1 into v is equivalent to m1 v1 cos theta 1 plus m2 v2 cos theta 2. Since a component of v1 and v2 will be along the x-axis. Taking the y directions, there was no displacement along y direction initially. So 0 is equivalent to m1 v1 sin theta 1 minus m2 v2 sin theta 2. The minus sign is taken in the second term because m1 v1 sin theta 1 is opposite to m2 v2 sin theta 2. And according to the conservation of kinetic energy, half m1 v square is equivalent to half m1 v1 square plus half m2 v2 square. It can be solved only if one of the variables is known. Hope you have understood about elastic and inelastic collisions in 1 and 2 dimensions. With this, we have come to an end of this chapter. Thank you, dear students.